Good afternoon, ladies and gentlemen. Today, I will present to you one study entitled Numerical Modeling of Structural Vibration with Piecewise Constant Material Properties using the Nodal discontinuous Galerkin method. My name is Indra Sihar, and I'm working with my supervisors Jieun and Maarten Hornikx. The content of this presentation is as follows. First, the background of this study is given. Then the governing equations I use to model the vibrations are presented, along with a brief explanation about the Nodal discontinuous Galerkin method. After that, the case studies, which is a T-shaped structure and a scale height with wooden floor, are presented along with their computational settings. Then the results of simulations are presented. Finally, the summary and further work on these applications are given. The background of this study is the trend in building construction, which has shifted from heavyweight to lightweight construction. Because of this, floors and walls can have poor sound insulation, especially in the low frequency range. To tackle this problem, good structural design is required, leading to an accurate predictive model. As part of this prediction model, we have used a wave-based numerical model to predict the vibrations of several lightweight structures. To solve this, we use the Nodal discontinuous Galerkin method. There are several reasons why we choose this method. The first reason is it can handle complex geometry because of the possibility of using unstructured meshes. Secondly, it can refine the numerical solution by increasing the number of elements or the order of the basis function. The third reason is DG method has an element-wise formulation and can be easily adapted for parallel calculations. Finally, the application of the DG method in the field of vibrations is still at an early stage, so we intend to make further contributions in this area of application. To model the vibrations of the structures, we use linear elasticity equations as follows. The equations are presented in a stress velocity formulation with 9 variables. The first 3 equations are the equations of motion, which express the relationship between the acceleration and the force resulting from the stress. The next 6 equations represent the relationship between the stress and the velocity gradient. These equations can be derived from the Hooke's law for an isotropic medium. Note also that on the right-hand side, there are the body force component and the viscous damping forces, which are proportional to the velocity to the damping coefficient zeta. These equations can be written in the following form, where F is the flux matrix. There are 4 independent mechanical properties here, namely the density, the modulus of elasticity, E, the Poisson ratio, mu, and the damping coefficient zeta. Recall that the material properties in these equations can also vary in space. In this study, the material properties are piecewise constant. In the Nodal DG method, the problem domain is discretized by k number of non-overlapping elements. This element is discontinuous, so the global solution of the partial differential equation is approximated by the summation of the local solution QH. On each element, the local solution is expanded by a Lagrange interpolation polynomial. In this work, the maximum polynomial order is n, and the tetrahedral elements are used to discretize the problem domain. Having this approximated solution, we can use the Galerkin methods for the residuals of the governing equations integration. In here, we obtain the strong form of the weighted residuals as follows. The second term on the right-hand side contains the numerical fluxes term, or F star. These numerical fluxes are important since it connects the local elements with the neighboring elements. In this study, the upwind numerical fluxes derive following the Rankine-Hugoniot jump conditions. Having all terms at hand, the semi-discrete form of the equations can be obtained. And to solve this, the Runge-Kutta integration method can be used. In this study, two impact vibration cases are simulated. The first case is the vibration of a T-shaped structure. This structure consists of two beams, the vertical and horizontal beam. Each of them is made of medium density fiberboard or MDF with different mechanical properties such as shown in the table. The black area on the picture denotes the fixed boundary condition on the vertical beam, and the rest of the surface are free boundary condition. The structure is excited at the location F, and four receivers are placed on the structure, including R4, which peak velocity in X direction. The second structure is the scale lightweight wooden floor. This structure consists of one plate with 7 joists with different mechanical properties. The excitation point is in the center of the floor, and the receiver points are distributed from the center to the corner. Each mechanical properties of these structures are obtained from the measurement. For the simulation, the impact excitation is given in the form of Ricker wavelet as follows. The wavelet has center frequency of 250 Hz, which is the center of the frequency of interest. The free and fixed boundary conditions for both structures are given by specifying the exterior values of the numerical fluxes on the boundary. For all simulation, the polynomial basis of order 3 is used, along with the CFL number equal to 1. For all simulations, the mobility of the structures are calculated. It is defined as the velocity divided by force. The index I in here shows the direction of velocity, and the index J shows the force direction. Here we present the meshes that are used for both structures. Different number of elements are used to check the convergence of the results, and each variation of the time step for the Runge-Kutta method is given. To validate the Nodal DG model, we conducted the real measurements for both structures. The figures on the left side show the measurement situation. It should be noted that prior to the assembly, we measured all the components of the structures to know their mechanical properties. In this measurement, each receiver signals were picked up using single-axis accelerometers, where the duration of the signals are 7 seconds with sampling frequency 51.2 kHz. The excitation is given using impact hammer, and the national instruments and MATLAB are used as the data acquisition systems. In a T-shaped structure, the horizontal and vertical beams are glued, and to have the fixed connection at the vertical beam, the beam was clamped to a massive concrete such as shown in the figure. In a scaled lightweight floor structure, the plate and each joist is connected using 9 equally spaced screws, and to have free boundary conditions on all surfaces, the scale lightweight wooden floor is hanged on 4 elastic ropes. Now we present the results of the Nodal DG simulation. First, we show the result of the T-shaped structure simulation. On the left figure, we show the convergence of the Nodal DG solution and their comparison to the FEM solution. In this figure, 3 mobility curves are shown at location R2. Each curve was obtained from the Nodal DG model with a different number of elements. Moreover, the changes of the natural frequencies within all different element numbers are less than 2 Hz, and it is assumed that the results have converged. The comparison with the FEM solutions show that the Nodal DG has a maximum difference of 15 Hz at the highest natural frequency. This is caused by the discontinuity of boundary condition at the black area in the right figure. In the FEM, the solution is continuous at the discontinuity, but in DG method, you can have 2 solutions at the same position due to its discontinuous solution. Moreover, the mobilities at four receivers are shown here. It can be seen that the mobilities obtained from the Nodal DG method closely match those obtained from the measurement. The table lists all of the natural frequencies. It can be seen that the sixth natural frequency having a maximum difference of 16.3 Hz from the measured value, which is about 3.8% deviation. These differences are assumed due to the isotropic properties of the structure, because it is known that the MDF material has a slight orthotropic property. The magnitude discrepancies are caused by inadequacy of the damping. The constant viscous damping cannot capture the frequency-dependent properties of the structure. For the frequencies below 150 Hz, it can be seen that the mobilities obtained by the DG method and the measurement is of the same order. However, the attenuation increases more rapidly with frequency in the experimental results. Secondly, we present the result of the lightweight wooden floor structure simulation. In here, we show three mobility curves at position C1 excited by the force at the center position. It is shown that the refinement by increasing element numbers from around 7,000 elements to 21,000 elements has achieved convergence. It will be shown later that changes in the natural frequencies are less than 2 Hz for all these cases. The mobilities at position C1 to C4 are presented here. As we can see that the mobilities obtained by the Nodal DG method agree well with the measurement result, especially in the frequency range between 20 to 250 Hz. Outside this range, the discrepancy increases. Similar to the previous case, the constant damping is one reason for this discrepancy, where the DG model does not capture the frequency-dependent damping of the structure. It can be seen that the first natural frequency at 15 Hz is heavily damped in the DG result, and the applied constant damping is too high for this frequency. In contrast, above 250 Hz, the damping from the experimental results become higher, and the peaks of the natural frequencies are no longer discernible. Another source of discrepancy is the connection between plate and joist. These components are connected by nails without glue, and in DG method, these connections are modeled as fixed connection, and this can lead to inaccuracies too. So in summary, the Nodal DG method has been applied to the vibration of the structures that have different material components. The variation of these material properties is treated using the numerical fluxes. And the simulation show that the agreement of the mobility to the measurement results is good. For the T-shaped structure, the natural frequency difference is less than 4%. For the scaled lightweight wooden floor, the natural frequency difference is lower than 6.4% in the range below 300 Hz. Moreover, we found that the current damping model is insufficient to represent the damping in broad frequency range. Further work is needed to improve this model. First is to incorporate the frequency-dependent damping into the model. Also, the method could be extended for the medium with anisotropic properties, as most lightweight structures have this property. So thank you for your attention, and now is time for question and answers.